Hi guys, welcome to this UKMT Senior Maths Challenge video, and today we'll be looking at the 2017 paper, questions 21 to 25. So let's start with question 21. It says, how many pairs xy of positive integers satisfy the equation 4 to the power of x equals y squared plus 15? We've got answers of a is 0, b is 1, c is 2, d is 4, and e is an infinite number. What we need to do for this question is we basically need to see how many pairs of solutions of x and y are equal to 15. It's kind of what we're saying. So if we rearrange this so we get 4 to the power of x minus y squared equals 15, what we can do is, we can rewrite 4 to the power of x, and we know that is 2 to the power of 2 to the x. So we say that 2 to the power of 2x minus y squared equals 15. Well, what you'll notice here is this is actually the difference of two squares. So we rewrite this as 2 to the power of x plus y, all multiplied by 2 to the power of x minus y equals 15. Then if you expand these brackets, you'll see we'll get 2 to the power of 2x minus 2xy plus 2xy, they cancel out, minus y squared, which means that we can write it in this form. What you'll notice here now is we've got two factors, if you like, that make up 15. The product of these two factors make up 15. So what we need to find is, what are all of the factors of 15? Well, we've got 15 and 1, and you've got 5 and 3, and that's it. So we need to set each of these factors equal to either of these equations. So the first one would be 2 to the power of x plus y equals 15. We could set the other equation to 2 to the power of x minus y equals 1. We need to see whether x and y will give us solutions which are integers. So let's try it. We can solve these simultaneously. So we can say that 2 to the power of x plus y equals 15. And 2 to the power of x minus y equals 1. What we can do is we can just add these two equations because they're both in the form of y. So that's going to give us 2 to the x plus 2 to the x, which is the same as saying 2 times 2 to the x. The y's are going to cancel out, and then you're just going to be left with 15 plus 1, which is 16. If we divide this equation through by 2, we're going to get 2 to the x equals 8. And from there, you should be able to see that x is 3. And then if we just substitute x equals 3 into one of these formulas for y, so let's say we rearrange this formula, so we get y equals 15 minus 2 to the x. And if we substitute x into this formula, it's going to be y equals 15 minus 2 cubed. Well, 2 cubed is 8, and 15 minus 8 is 7. So we get x equals 3 and y equals 7. So that is one pair of integer solutions. Now, let's test the factors of 5 and 3 to see whether we'll get integer solutions for x and y. So we do the exact same thing. We say that 2x plus y is equal to 5 and 2x minus y is equal to 3. Add the two equations together, you get 2 multiplied by 2 to the x equals 8. Divide through by 2, you get 2 to the x equals 4. And from there you should be able to see that x is 2. Rearrange this top equation, you get y equals 5 minus 2 to the x. Substitute for x equals 2, you get y equals 5 minus 2 squared. Well, 2 squared is obviously 4, and 5 minus 4 is 1. So we get x equals 2 and y equals 1, which is another pair of integer solutions for x and y. So therefore, we've got two pairs of positive integers which satisfy the equation 4 to the power of x equals y squared plus 15. So therefore our answer is C. Question 22. The diagram shows a regular octagon and a square formed by drawing 4 diagonals of the octagon. The edges of the square have length 1. What is the area of the octagon? We've got answers of A is root 6 over 2, B is 4 over 3, C 7 over 5, D root 2, and E 3 over 2. Okay, so we know that the lengths of this square are 1. Okay, and we need to find the area of the octagon. So of course that's the area of this whole shape. Well, we know what the area of the square is, that's easy. The area of the square is 1. But of course we don't have a formula to find the area of the whole octagon. But what we can do is we can find the area of these triangles. And in order to do that, well, we can see, if I zoom in, these sides are of course the same length, which means that these angles are going to be the same, which means it's an isosceles triangle. And if it's an isosceles triangle, well, then I can divide this into 2 right-angled triangles. So that means I need to find the base of these 2 right-angled triangles, this length here. So the way I thought about this is, well, what if I rotate this square 45 degrees anti-clockwise? Okay, so if I rotate it 45 degrees anti-clockwise, it's going to look something like this. And what that means is, well, that this diagonal is equal to this diagonal. And I need to work out the length of that diagonal in order to get the length of those 2 smaller right-angled triangles. Well, that's easy to find out the length of this diagonal because I can just use Pythagoras' theorem. So if I just get rid of this, so of course we can use Pythagoras' theorem to work out the length of that diagonal. So we can do equal to the square root of 1 squared plus 1 squared, which is the square root of 2. So the diagonal is root 2, which means that this length is also root 2. The square we know is symmetrical. We know that the octagon is symmetrical. The square has 4 lines of symmetry, the octagon has 8 lines of symmetry. So of course what that means is those 2 lengths that I've highlighted, they're going to be equal. And if we know that the side length of this square is 1, we can work out what these length of those yellow lines are going to be. Well, it's going to be obviously root 2 minus 1. And then of course they're equal, so we can just divide them by 2. Okay, because that's good, because now I've got the height of my triangle. And of course we know what the area of a right-angled triangle is, half base times height. On my base, this length here is going to be 1, because that's the length of the square. So I can say half times 1. And then the height is what I've just worked out here, root 2 minus 1 over 2. So I can just say multiply by root 2 minus 1 over 2. Well, that's easy. That's just going to be root 2 minus 1 over 4. And of course, all of these 4 triangles around the outside of this square are equal. So I can just multiply this root 2 minus 1 over 4 by 4. And that gives me root 2 minus 1. Okay, so what that means is I've got the areas of all these triangles around the outside. I don't want the area of all the triangles around the outside. I want the area of the triangles around the outside and the area of the square. So all I need to do is just add the area of the square. So it's root 2 minus 1 plus 1, which is root 2. And I've got an answer for root 2, which is D. So therefore, answer equals D. Question 23. The parabola with equation y equals x squared is reflected in the line with equation y equals x plus 2. Which of the following is the equation of the reflected parabola? We've got answers as A is x equals y squared plus 4y plus 2. Got B is x equals y squared plus 4y minus 2. C is x equals y squared minus 4y plus 2. D is x equals y squared minus 4y minus 2. And E is x equals y squared plus 2. So what I've done is I've drawn a sketch of both the equations y equals x squared and y equals x plus 2. I think the first thing we should do is find the points at which these 2 equations intersect. So if we make x squared equal to x plus 2, then we get x squared minus x minus 2 equals 0. We're going to get factors of 2 and 1, and that's going to factorise to x minus 2 bracket x plus 1 equals 0. So we're going to have x equals 2 or x equals minus 1 as our values for x. We can then work out our values for y by substituting these values into the equation y equals x squared. So we're going to get y equals 4 or y equals 1. So we've got coordinates 2, 4 and minus 1, 1. So minus 1, 1 is here, and the 0.24 is there. Okay, that's good, because what's going to happen is when we reflect the curve y equals x squared in the line y equals x plus 2, the reflected curve of y equals x squared is still going to have the intersection of these 2 points. So the way I thought about this question was, if we take a point, let's say here, and call it xy, well, when it's reflected in the line y equals x plus 2, let's think what happens to the x-coordinate and the y-coordinate separately. So the x-coordinate is going to be translated to y minus 2, okay, because just the equation y equals x plus 2 rearranged. And of course the y-coordinate is going to be translated to x plus 2. So we roughly draw that coordinate. So we're going to go down by minus 2, and then we're going to go across 2. Let's say our coordinate is roughly here. It doesn't really matter, it's only a sketch. But yeah, we could say that is our coordinate there. So if that's our coordinate, I can now draw a rough sketch of what the reflected curve is going to look like. So I need to go through both the points of intersection, and then back through y minus 2, x plus 2. It's not a great sketch, but you get the idea. The question doesn't say to sketch the curve, it says to find the equation. Well, if these are the 2 new points, then surely those points lie on the equation of the reflected curve. So we can substitute these points into the equation y equals x squared. Y equals x squared. Y is now an x plus 2, and x is y minus 2 all squared. If we expand brackets, we're going to get y squared minus 2y minus 2y, which is minus 4y, plus 4. And then if we look at our answers, they're all in the form of x equals some function of y. So we can just minus 2 from both sides. So we get x equals y squared minus 4y plus 2. And that is one of our answers. It's answer C. So therefore, answer equals C. Question 24. There is a set of straight lines in a plane such that each line intersects exactly 10 others. Which of the following could not be the number of lines in that set? We've got answers of A is 11, B is 12, C is 15, D is 16, and E is 20. So if we say that the lines in any given set are represented by the letter L, then what we know is that the only straight lines in the plane which don't intersect are those lines that are parallel. And we can say that our parallel lines are going to be equal to L minus 10. But of course this is only for one set, and within this set there's going to be a whole series of different subsets. What we can say, if we represent a parallel line to be P, so P equals L minus 10, then we can say a line is equal to n times P, where n is our total number of subsets and P is our number of parallel lines. So within the whole set, if we say that there are NP lines, then surely there must be NP minus P parallel lines. And if there's NP minus P parallel lines, we can say that NP minus P lines in a set is equal to the 10 other intersections. So we make NP minus P equals 10, take out a factor of P, and we've got that as our equation. So now what we need to do is we need to think, well, this P multiplied by this n minus 1 represents 2 factors of 10. So if we write down all the factors of 10, which we know, which are 1 and 10, 2 and 5, but remember we could also have 5 and 2 and 10 and 1, because we could have P as 1 and n minus 1 as 10, or we could have n minus 1 as 1 and P as 10. So that is something that we need to consider. So what we can do is, if we draw a table and call this n minus 1, call this P, then from these factors we can work out what n is, and then we can work out what the product of NP is. And if we can work out what MP is, then we can work out all the lines which intersect exactly 10 other lines. We go through each of these. Start with n minus 1 is 1, so that means P will be 10. We can write 2 for n minus 1 and P is 5, n minus 1 is 5 and P is 2, and n minus 1 is 10, P is 1. So we can easily work out n because we've got our values for n minus 1, so we just need to add 1 to each of those terms. So that's going to be 2, 3, 6 and 11. Now we can work out all of the lines which intersect 10 other lines by working out the product of n and p. That's going to be 10 times 2, which is 20, 5 times 3 is 15, 6 times 2 is 12, and 1 times 11 is 11. If we look at our answers, 20 is E, 15 is C, 12 is B, and 11 is A. Only answer on here, which could not be the number of lines within the set, is D is 16. So that must be our answer. So therefore, our answer equals D. Question 25, the final question. The diagram shows a regular nonagon N moving clockwise around N. At each vertex, a line segment is drawn perpendicular to the preceding edge. This produces a smaller nonagon S, shown shaded. What fraction of the area of N is the area of S? We've got answers as A is 1 minus cos 40 all over 1 plus cos 40. We've got B is cos 40 all over 1 plus cos 40. C is sine 40 over 1 plus sine 40. D is 1 minus sine 40 all over 1 plus sine 40, or E is 1/9. Okay, so when I looked at this diagram, the first thing I noticed is that the nonagon of N is similar to the nonagon of S. So I thought, well, let's introduce two different variables. Let's call this side X and the side of the smaller nonagon Y. And we need to find what fraction of the area of N is the area of S. So we can write the ratio of S to N as Y to X. But that would be correct if it was for the length. We want the area. So the area is going to be represented by the ratio Y squared to X squared. And we can rewrite this as Y squared over X squared. So what we need to do is we need to find an expression which is either in terms of cos or sine, or it might even be equal to 1/9, which is equal to Y squared over X squared. So what I've done is I've drawn another diagram which focuses on two right angled triangles which make up the nonagon N. So this is the diagram. As you can see, up here I've got the smaller nonagon S, and here I've drawn two right angled triangles that make up N. Right, N here. And as you can see, we've got X here as our side length for N, and Y, which is our edge for S. So that's also going to be Y, and that's going to be Y. We need a bit more information for these right angled triangles because we don't know what the height is, or we don't know what the hypotenuse is. So let's just introduce another variable, and I'm going to call that variable H for the height. So that's going to be H. This is H. We can say our hypotenuse is therefore Y plus H. Now, there's something else we can do. We know that a nonagon is a 9-sided shape. We can work out what the exterior angles of the nonagon S are going to be. Well, that's easy. We can just do 360 degrees divided by 9, which is 40. And what you'll find is the exterior angles are going to be this angle and this angle. And of course, the interior angles of S will be 140 and 140. So now we've got quite a bit more information going on in this diagram than we did have. But let's take what we know about right angled triangles. We know that the adjacent side squared plus the opposite side squared equals the hypotenuse squared, which obviously corresponds to Pythagoras' theorem. So we can write an equation which says that x squared plus h squared equals y plus h all squared. If we expand those brackets, we get y squared plus 2hy plus h squared. H squareds cancel each other out, and we're left with x squared equals y squared plus 2hy. Now, we want an equation which is in the form y squared over x squared. Well, we can divide both sides of this equation by y squared, and we get x squared over y squared equals y squared plus 2hy over y squared. Now on this right hand side, if you rewrite that as y squared over y squared plus 2hy over y squared, that obviously becomes 1, and that becomes plus 2h over y. And of course you can rewrite that as y plus 2h all over y. So x squared over y squared equals y plus 2h over y, but we want y squared over x squared. So we can just flip these fractions over, get y squared over x squared equals y over y plus 2h. Okay, that's good. But y and h are variables that we've introduced. And of course our answers, whether they're in the form of cos and sine, they don't include our variables. So we need to work out what are the actual values of y and h. Well, we know what our opposite angle is now in our right angle triangle. We know it's 40. So we can write an equation in terms of x and h and cos 40. So using basic trigonometry, you can say that cos 40 is equal to adjacent divided by our hypotenuse. So our adjacent side is h and our hypotenuse is y plus h. So h over y plus h. And what you'll see is if we rewrite this bottom fraction, instead of y plus 2h, we write it as y plus h plus h. The term y plus h is the same term that we've got in this equation. So that means we can make y plus h our subject for this equation. So we can say y plus h equals h over cos 40. And then of course we can also get a value for y, because y is just going to be h over cos 40 minus h. So if we substitute these expressions into our equation for y squared over x squared, what that will mean is our expression won't include any terms within y, they will all be with respect to h, and hopefully the variable h will cancel itself out, but we'll see. So y squared over x squared equals y. Y is h over cos 40 minus h. Now that is all divided by y plus h, which is h cos 40, then plus h. If we look at the numerator and denominator separately, let's have a look at this top line. There's going to be a common denominator of cos 40. So if you multiply top and bottom by cos 40, and I'm going to do the same for this bottom equation actually, because they've both got common denominators of cos 40, just so it makes it a bit more easier. We're going to get y squared over x squared equals h minus h cos 40 all over cos 40 all over h plus h cos 40 all over cos 40. Now, it's looking very messy with these fractions, but what you should know is if you've got a fraction divided by another fraction, it's the same as doing the first fraction times the reciprocal of the second fraction. So we can rewrite it in that form. So we can say y squared over x squared equals h minus h cos 40 over cos 40 times the reciprocal, so cos 40 over h plus h cos 40. And then, of course, you'll notice that the cos 40s cancel each other out. And you're left with y squared over x squared equals h minus h cos 40 all over h plus h cos 40. And what you should notice is that there is a common factor of h, which is what we want, because we don't want h within our expression, because h was just a variable that we created. So we take out a factor of h from the top and the bottom. You'll see that those h's cancel out, and you are left with y squared over x squared equals 1 minus cos 40 over 1 plus cos 40, which I've definitely seen as one of our answers. And if we scroll up to the top, that is answer A. So we can say, therefore, our answer equals A. And that is the 2017 UKMT Senior Maths Challenge paper completed. Any questions that you've got, feel free to leave a comment down below, and don't forget to subscribe to the channel. Thank you very much for watching.